Now, because it wasn't touched on a whole lot in the previous video, I do want to do one example regarding residual plots. Now, this one's from the 2016 VCAA Exam 2, and it's question 3D. I really like this question because the two pieces of information it is asking from you are essentially the two key, most important things you need to know about what this residual plot is for and what information you can gather from it. So knowing how to answer these two questions is really important. It's the two key pieces of information you need. The first question says a residual plot can be used to test an assumption about the nature of the association between two numerical variables. What is this assumption? So what we're testing is that the assumption that the association is linear. That's what we're testing. That's what the residual plot is for, to test whether our assumption that the linear association is appropriate. Now, does this particular residual plot support this assumption? And let's explain the answer. Yes, it does, because there is no clear pattern. We could also say the residuals are random. So these are the two key pieces of information that we need to know. The residual plot is used to test the assumption that the association between the two variables was linear to begin with. And we know if this assumption is appropriate if the residual plot has no clear pattern. Sometimes you may see a residual plot where the residuals, they've got a linear pattern. Maybe they're going upwards, maybe they're going downwards. Often you may see that the residuals seem to be curved, okay? If you do notice a clear pattern in the residuals, then perhaps the association between the two numerical variables should never have been considered to be linear in the first place. But because there's no clear pattern, then we know that we can assume that their association is linear. Now let's look at completing a full regression analysis from some raw data. We had a class of 16 students that were asked what percentage of the practice questions they completed before a test. These percentages and their test results are shown below. Compile a regression analysis report. The first step in our regression analysis report is to describe the association, and to be able to do that we need to draw up a scatter plot. And before we do that, we should be deciding which one is going to be our response variable and which one is our explanatory variable. The way that this is worded suggests that we can predict the results of a test based on how much practice they did. So practice is our explanatory variable and results is our response variable. Because practice is our explanatory variable, which is typically on the x-axis, I'm going to put it in this first column because x usually comes first. So this one will be practice. And this one will be results. Once we've entered our data, to set up our scatter plot, we go to this one here. We've got our x and y's. We set that and this button to draw the scatter plot. There's a few characteristics that we can decide just by looking at it. We can see that there is a slight positive trend here. So the association is positive and it does seem to be linear. So we've got a positive linear association, but it's difficult to say exactly how strong this is. Is it strong, moderate, or weak? To do that, let's figure out what our correlation coefficient is. We've got our correlation coefficient R being 0.593 to 3 significant figures. Now, if we think back to our chapter 3 notes, a correlation coefficient of 0.593 corresponds to a moderate positive association. So we can put that in words ready for our regression analysis report as, from the scatter plot, we see that there is a moderate positive linear association between test results and the practice amount, with the correlation coefficient equaling 0.593. There are no positive outliers. The next step in the report is to determine the least squares regression equation. Now this is really easy. We're already in the right spot after getting our correlation coefficient. We've got our A and B values here, remembering that it is in the form of y equals ax plus b. Also remembering that we should not leave it as y and x. We should replace y and x with our explanatory and response variables. So our least squares regression equation, if we start with our y value, which is our results, we have the results of the test equal A, which is 0.486 to 3 significant figures, multiplied by practice, plus our B value, 25.7 to 3 significant figures. Now, getting that ready for our report, we have the equation of the least squares regression line is results equals 0.486 multiplied by practice plus 25.7. Our next step is to interpret the slope and the intercept. Let's start by looking at the slope. We can see by looking at this equation, each time practice goes up by 1%, we're going to be adding 0.486 to the results. To put this in words, we have the slope of the regression line predicts that, on average, a 1% increase in practice results in a 0.486 increase in a student's test results. So every time they increase their practice percentage, their results go up by 0.486%. Now, what the intercept predicts, we get our intercept value when practice equals 0. So if a student did not practice at all and practice was equal to 0%, results would equal 25.7. So the intercept predicts that, on average, a student's test result would be 25.7% if they did not practice at all. Step 4 is to interpret what the coefficient of determination means for this association. We can get to our coefficient of determination the same way we've been getting to our other important pieces of information so far. We have the R squared, or coefficient of determination value, equal to 0.351 to 3 significant figures. Or you can write that as 35.1%. In our report, this will be worded as the coefficient of determination indicates that 35.1% of the variation in results is explained by the variation in practice. You could choose to add on that the remaining percentage is explained by some other factors. Now, we would get our remaining percentage. Obviously, 100% is the total. So you could add on the remaining 64.9% can be explained by other factors such as, and then you would include what are the factors you think would be suitable for this particular situation. Now, the very last piece of our puzzle is the residual plot. We want to use the residual plot to see whether assuming that the association was linear in the first place was actually appropriate. To get your residual plot up on your calculator, we first go to the familiar spot, Calc, Regression, Linear Regression. Ensure that you're selecting your correct X and Y variables. Now, this copy residual part, you want to put it in list 3. What that's going to do is it's going to essentially fill list 3 with all the residuals. When we hit OK, and then OK again, we see list 3 fill up with all the residuals. Let's get rid of that scatter plot for now. Now what we want to do, we want to draw up a scatter plot with our residuals versus whatever our explanatory variable is. So it'll be practice versus list 3 here. To set that up, we go to our usual setup graph one. We leave our X variable, but we want to change our Y variable to list 3 so it plots the residual plot. Set that up and click this one to view it. Now we've got our residual plot here on our calculator. Now, in order for the assumption of linearity to be appropriate, we need the residual plot to have no clear pattern. Now, I can't see any clear pattern here. It does not look like the residuals are tending upwards in any direction. They're not tending downwards. I don't see any curves anywhere. Therefore, I think the assumption that the association between our variables was linear is appropriate. So in our report, we will word this by saying the lack of a clear pattern in the residual plot confirms the assumption of a linear association between the practice amount and test results. Now, just quickly, something I didn't quite touch on, I forgot to mention. The coefficient of determination, where we say the coefficient of determination indicates that 35.1% of the variation in results is explained by the variation in practice, that does not seem like a lot. It kind of makes, this low percentage makes it seem like, well, they mustn't be very related. But it should be stressed that a coefficient of determination above 30% is regarded as being highly predictive. So if you have a coefficient of determination more than 30%, then your linear association is highly predictive, and you can use your least squares regression line to make highly predictive predictions. Here, I've put all of my report pieces of the puzzle together, all the pieces I wrote in black along this video. Put them all together for the full report that you can read here.